This is my submission for assignment 2.2, Kinetically Challenged in Physics. What we have here is a 3-link robotic arm. We can use either forward or inverse kinematics. The industry standard is to use inverse kinematics. A brief description of inverse kinematics is that instead of solving each angle to define the end effector position, we have a point in space where we want the arm to reach. So we have a known point, which is 0.4. This is our target point. We have 0.3, which is our end effector. We have 0.2, which is the end of segment 2 and the base of segment 3. We have 0.1, which is the base of segment 2 and the end of segment 1, and then we have 0.0, which is our origination point. The math used is taken from opentextbooks.clemson.edu. The chapter 3, inverse kinematics, modeling, motion planning, and control of manipulators and mobile robots. Most of what we have is taken from 3.2, analytic approach, geometric approach, and then we have some taken from 3.4 in kinematic decoupling and inverse orientation. There's a 3-link example in the practice questions at the bottom, which we use to figure out our equations. So we start with global variable phi. This is the angle between 0.0 and 0.4. Can't see 0.4, but it's there. See it glowing right there, glowing dot. That's 0.4. So phi is the angle along this x-axis from 0 to 4. And then with inverse kinematics, what we do is we start with 0.4. We match up 0.3 to 0.4. We orient segment 3 so that it is always pointing at 0.4 from its base, which is 0.2. So you'll see as we move 0.4 up or down, that segment 3 is always oriented towards 0.4. Then we work our way backwards from theta 3 to theta 2. Theta 2 is describing the angle from 0.1 to 0.2. And then theta 1, which is describing the angle from 0.0 to 0.1. If you think about this from a XY position, each point has its own XY coordinates and its own XY plane. So 0.0 is on the normal XY plane, so this would be Y0, X0. 0.1 would have Y1 and Y2, which is X on the 0.1 plane is collinear with segment 1's orientation. 0.2 has a XY plane where X is collinear with segment 2 and Y is perpendicular. And finally, X3 is collinear with segment 3 with X3 perpendicular. To find the different angles, we go in reverse, like I said. So we go from theta 3, which theta 3 is the same as phi 1. And so we just plug in phi to theta 3 to find our theta 3. and you'll find that equation right here. So R2 defines the orientation. That's the attitude. Is it pointing up or pointing down? So if we were to change this to negative, it would drop 0.2 down below here, so that would be pointing up, and the attitude of the third segment would always be in the upward position as it's seen on this 2D plane. Next, we solve for theta 2. This is taken directly from the analytic approach, 3.2, 3.2.1. So R2 minus L1 squared minus L2 squared divided by 2 times L1 times L2 equals C2. Now this is C2 raw, R-A-W, raw. And we use a, what's the word? Decoupler right here, because C2 must always equal or less than 1. So then we plug in C2a to cosine, and we get theta 2. Then we take theta 2 to find theta 1. Theta 1 is defined as a tan 2 with the orientation of the third segment, a tan 2, L2, so segment 2 sine theta 2, and then L1 plus L2 cosine theta 2. That defines our angle for theta 1. So to find the actual theta 1, we actually do theta 1 plus theta 2. Or excuse me, theta 1 is just theta 1 on its own. And then to find theta 2, we find it by adding theta 1 plus theta 2. That's theta 2. And then theta 3 is theta 1 plus theta 2 plus theta 3. So if you think about it from a circle perspective, we have 360 degrees. We're using radians, but in this case, to simplify it, I'll use degrees. So let's say that our angle is $90 degrees from 0. So this would be somewhere close to 90 degrees for 0.4 from 0.0. What that means is that theta 3 must equal 90. And so theta 1 plus theta 2 plus theta 3 must equal 90. But for simplification, we can just make our end effectors theta equal the global phi. And that is my presentation for assignment 2.2 kinematic challenge, or challenge, kinematically challenged. I forgot. Anyways, hope you enjoyed it.